I prepared this talk about a week ago. It's very recent. It's about matrix multiplications, which power most of the AI workloads these days. This talk, I think, was originally intended for like an hour-plus format. And I also wanted to add like a few more things, but maybe I'll just like gloss over them in voice if you'd be interested. I think there are not many of us here, so feel free to stop me at any point and just ask questions randomly. Would be more fun. Yeah, and we have a mic. Perfect. So, is the clicker working or not really? Okay, let's just use the buttons. So, why do I care about matrix multiplications? We kind of live in a world where matrix multiplications are responsible for a very significant chunk of compute time on all of the chips. So practically, easily hundreds of billions of dollars of CapEx is spent on matrix multiplications. When we program matrix multiplications, especially like in AI community or within scripting workloads, we generally use libraries like NumPy. It's a very well-known standard. Sadly, NumPy is just a convenience wrapper around the libraries that actually do the heavy lifting. More than that, NumPy is actually not as portable as people think. So Python supports up to 115 platforms for every package release on PyPI. PyPI, I guess. And NumPy only delivers maybe like 50. The libraries that I maintain ship all 115 platforms supported and more, and they target not only Python, but also C, C++, Rust, Swift, other languages as well, and they're oftentimes implemented in assembly. And what's maybe even more important for the conversation that we're having today about AI is that they're designed with mixed precision in mind. So almost everything that happens in high-performance computing these days, and especially in AI workloads, is not really computed with one level of precision or with a single numeric type. So it's not like we just have a floating point number that is like 32 bits or 64 bits. We put it in and all of the computation happens on that same level of precision. No, every different part of the computation happens at different levels of precision. So designing systems that can actually take advantage of low precision numeric types and also leverage high precision types when needed is highly non-trivial. And that's something that I spent the last decade of my life working on, among other things. And all of it is maintained as a bunch of open source libraries that you most likely are never interacting with directly, but probably use under the hood of all the products that you use daily. So there are many, many types of matrix multiplications. Just a bit of nomenclature, like some of them are called sparse when the input is a sparse matrix with most entries are like 0. We're not going to cover those, too complicated for a talk. Oftentimes when you run matrix multiplications and the matrices are getting larger and larger, you may split the same matrix between many, many GPUs or many devices. It's like separate nodes, servers across your cluster. We're not going to talk about this. But this is what happens sometimes when you do like model level parallelism when doing, let's say, inference of different large AI models. It's like a single layer may not even fit entirely on the same card, so you split it in different ways between multiple cards or multiple machines. And then there are like really smart algorithms for matrix multiplications. That's part of like theoretical computer science research. And there's been ongoing research for the last 30, 40 years on how to do matrix multiplications more efficiently, how many numeric operations it takes to take two, let's say, square-shaped tiles, n by n, and multiply them. And turns out you can go below cubic time. But we're not going to talk about that because those algorithms, amazing in theory, are not very practical in everyday problems. And then one other aspect is like where the memory is located, where is the matrix itself? Is it in random access memory or like GPU's video random access memory? Or is it somewhere outside in external memory? So external memory algorithms are much more complicated. We'll not cover them. And we'll focus on the simplest case possible, dense matrix multiplications on a single node, really dumb algorithms, everything stored in memory, but we'll cover mixed precision types. So Matrix multiplications in theory sound super simple, especially like the dense case. We have 3 nested for loops. We go through them, and with this simple line of Python, we accumulate the value of Cij as a dot product of Aik and Bkj. So take the rows of first matrix, multiply by the columns of the second to get a specific value of the third matrix. Super simple. In reality, it actually gets much more complicated. The very first thing that we will not really cover is something that high-performance computing engineers have known for like 20, 30 years, that you need to tile the matrices for cache efficiency. So your CPU and your GPU has SRAM and other small chips that are much higher bandwidth than video random access memory. So let's say when you go to the store and buy your next GPU, and it says hopefully 140 gigabytes like the H200s that I'm currently using, 140 gigabytes is not exactly the memory that will be responsible for the most of throughput, because if your algorithms are implemented wisely, you will not be fetching the data from that huge memory bank all the time. You'll be actually fetching memory from SRAM modules closer to the arithmetical logical units on your machine. And to be able to saturate SRAM properly and reduce the latency of memory access, what you do is you tile the matrices. So the visuals I shamelessly stole from a guy who's currently at Anthropic, and he gave this intro talk on like how we used to do matrix multiplications. It's a very interesting article, very well visualized. You may want to go check it out. The QR code will take you there. It's in the bottom right corner. But luckily, matrix multiplications, especially the dense dumb ones that we're covering today, are such a prolific topic that every great visualizer on internet has already tried to cover and has done a great job at, much better than I can do. So the very nested part of the matrix multiplication, once we go from Python to C, looks more like this. We've fetched the tiles of matrices into the shared memory, and then within the most nested loop, we have some form of calculating a thread-specific result, which will use some really weird, ugly indexing mechanic on like how to locate a specifically indexed tensor element within a larger memory bank. It will be fetched and multiplied again. Luckily, it's not how it's. We currently do like a more advanced thing than that, and there's been a great talk or like a great blog post that improves on the blog post that I've just mentioned. So the blog post that I've just mentioned does 30 teraflops. And if you look at the data sheets of the GPUs that we buy these days, 30 teraflops is not that crazy. 30 teraflops, so tera is 1,000 times bigger than giga, so it's 10 to the power 12. So it's 10 to the power 12 operations per second in a single teraflop. 30 teraflops is, of course, 30 times bigger. The way to get to like proper utilization of modern GPUs, so in this case, grow by a factor of 20 in throughput, you need to use a few different techniques. The author of the next blog post, Pranjal, he covers 10 of them. Not all of them are equally relevant. The 4 that I find the most interesting are obviously tensor cores. If you've watched any one of the NVIDIA's talks from 2017 onwards, every year at GTC they talk about the new tensor cores. So there's a specialized pieces of silicon that are responsible for tiled matrix multiplications. This is what gave an immediate boost from 30 teraflops to 300. So definitely check out your manuals to learn how to use those. Asynchronous loads, so practically like almost a hardware level abstraction for asynchrony. This is something that most CPU side or host side developers have never seen, because like we deal with concurrency and with asynchrony at the software level, not at the hardware level. But when you're going for a petaflop, so 10 to the 15th power of throughput, you should actually think about asynchrony at the hardware level. And then there's a cool trick about hiding store latency. Last but not the least, we'll probably not talk about Hilbert curves. But if you're a math nerd like I am, then we can talk about this afterwards. So tensor cores have been around for several years, since 2017. We're now seeing their 5th generations with Blackwell chips coming out. So the B200s or the GB200s, the Grace Hopper super chips are going to feature 5th generation cores. They don't support all numeric types, so it's not like you can immediately use those things for every kind of matrix multiplication. The silicon budget is limited. It's not every numeric type that gets the equal amount of attention. At start, with the voltage generation GPUs in 2017, Float64 was not relevant at all to NVIDIA, so they kind of skipped the whole supercomputing market and went directly for like half precision Float16 numeric types. The reason this looks kind of weird is because if you go to like Python and most numeric high-level libraries, they don't even have a specification for low precision numeric types. So I constantly rant about this on NumPy's GitHub, that even when like accelerated library developers try to prove some form of compatibility with NumPy, NumPy doesn't just avoid efficient kernels, it doesn't have an interface to define them. So there is no way for you to pass like low precision types to NumPy. There is half-baked support for Float16, there is nothing for bfloat16, there are no complex numbers of low precision, and so on. So well, then we got the Ampere cards, like A100s, and afterwards, of course, the H100s, the Hopper generation, that is responsible for the bulk of NVIDIA's shipments. And as you can see, the throughput goes up within like most generations, but we also get a wider support for different numeric types. Sadly, the data sheets that are being shared by those vendors are often misleading and inaccurate. So they would oftentimes include numbers for sparsity rather than, or like structured sparsity rather than the dense matrix multiplications. And structured sparsity is almost never used. There are all kinds of other numeric types that are not properly covered by data sheets or even the hardware support, like half-byte int4. It's just 4 bits. It was kind of introduced a generation ago, but then only lived for 1 generation. And like there is no proper new support. FP4 and FP6 are very new things with Blackwell. There's like 100 ways to use them. Those are like some of the longest assembly instructions, almost impossible to program. And then even for FP8, NVIDIA has 2 numeric types, E5 M2 and E4 M3, which are 5-bit exponent and 2-bit mantissa, and 4-bit exponent and 3-bit mantissa. But if you learn about those types and you may know how to program them, it doesn't mean you can program on other vendors, because there are competing standards from other chip makers, including here in the UK. To make things worse, those numeric types are not what they seem. So TF32, you may think as a 32-bit, some kind of weird numeric format. No, it's not. TF32 is actually 19 bits, not even 16. And it has the exponent that is the size of BF16 and the mantissa that is the size of FP16, so a really weird hybrid format. FP8 is not better. And if you want to like just understand how this changes between generations, sadly, there is no good ground source of truth, maybe except for the Wikipedia page for CUDA, because the data sheets are very fragmented and the tables are not uniform. They contain very different pieces of information that you will have to stitch yourself. NVIDIA was not the only vendor to realize the relevance of matrix multiplications, despite the public picture. They're not the only ones that do chips for AI and for compute. Every single hardware vendor today has some form of matrix multiplication support in their hardware. Apple has 3 fast ways to do matrix multiplications on their chips, if one wasn't good enough. And all 3 of them are really hard to program, to be honest. So NVIDIA has MMA instructions since Volta, but they're practically deprecated with Hopper. So like on Hopper, you need to use TC Gen 5 instructions. So software is not really backward or forward compatible. You need to target every architecture separately. AMD CPUs today, I think still the best way to program them is AVX512, the instruction set that is shared between Intel and AMD, or like the set of extensions. Before Zen 5, Turin chips, even on Genoa, they're emulated. So in reality, those are not 512-bit chunks of data. Those are 2 256-bit chunks that are emulated by CPU to look like they're bigger. On Apple, as I said, 3 weird ways to multiply matrices, and practically none of them are documented. So good luck reverse engineering. On Intel CPUs, it's actually quite interesting. So Intel has shrunk in its market value more than any other chip maker in the last few years. I think they're now maybe like worth less than they were worth in '80s. So it's kind of a remarkable track record for the stock. That said, on like matrix multiplication side, they have like some of the most programmable chips, and you can actually get your hands on them. You can actually rent them on AWS for just $1 an hour, $1 an hour. And you can immediately program with AMX for half precision numerics. You can multiply int8 matrices, and with next-gen Granite Rapids, we're about to get BrainFloat 16 support. So the reason AMX is like so interesting is because, of course, like it's so programmable. Most of our software is already on the CPU. You don't need to learn CUDA. You just need to add a couple of weird instructions to leverage all of this. Sadly, when you go through their data sheets, again, they don't know how to compare their hardware properly. And their marketing team just like intentionally tries to fool everyone else. So instead of just properly comparing the current generation chips to the previous one and declaring a good improvement, they try to compare to something really old and obscure everyone reading this. So because of that, I took a freaking month of my life to actually write down a bunch of benchmarks with software development best practices for matrix multiplications and not just for them. And I called the project Less Slow, and I have analogs for Python and Rust. And what Less Slow does is kind of adds a mixture of assembly for x86, for ARM, and for CUDA for different generations, C++, and the CUDA C++ as well, and a bunch of C code to showcase what are the pitfalls of programming this kind of stuff. And one of the first things that I did, of course, I tried to profile AMX, comparing it against AVX 512, the instruction set that we used to have like even before. Yes, we get fewer registers, so not 32, but instead 8. But on the bright side, those registers are a lot larger. So instead of being 512 bits or 64 bytes, they're 1,024 bytes. So it's a kilobyte-sized CPU register, huge, massive registers. Their latency is higher, but when we look at the throughput and we measure it ourselves, we can see that, like in this last column, for int8, it's possible to squeeze 700 teraflops of throughput in those kinds of operations from a CPU. So people really love to separate CPUs and GPUs a lot. Their design is not as different as people think, especially as we get to those like super large registers. That said, you have to be precise with like the way you code them, because like let's say if you have denormal floating point values, so those are like some really weird values, you may accidentally notice that on Intel the CPU performance will drop to 0.6 teraflops. So this is 3 orders of magnitude reduction compared to the number that we have over here on the right. So 0.6 on the left, 683 over here. Again, for all of those tricks and like how to avoid the pitfalls, go to the repository. And then it doesn't stop with a one benchmark, because like I maintain maybe like 10, 20 open source projects, and just crossed 10,000 stars, by the way, this week. Hooray! I also maintain like this small micro repository that I come back to every 5 years to update it with some tutorials on high performance computing. I think I first wrote it in early 2010s when I was just like playing around 2010 with OpenGL, OpenCL, and CUDA, and then I updated it around like mid 2010s, and I gave a few talks on this in late 2010s, and now I updated it again, so the project will never die. One new thing that I added here is like this latency hiding. And if you have exceptional memory, which of course all of us do, we all remember that a couple of slides ago, one of the articles about cuBLAST performance mentioned latency hiding. So latency hiding is one of the least explored techniques, even in high-performance programming, let alone the rest of the programming. So what it essentially means on the chip side, different parts of silicon are responsible for different operations. So even when you look at the CPU, there are multiple ports, and not all of the operations can execute on all of the ports. So there are many, many layers of parallelism, maybe 10 times more than most developers ever interact with. And one of those layers at practically the very bottom is port utilization. So I found this fun, cool thing on AMD Zen 4 that you can actually use weird kinds of instructions that are not intended for a specific workload to double your throughput towards actually 330 gigabytes per second on a single core. So even on the CPU side, even AMX aside, there's like ways for us to achieve much higher throughput than what we may see in some of the data sheets. The things didn't stop here. On one of my older C slides, we saw a really complicated way of counting the address of a specific byte in a buffer to kind of fetch it into memory. NVIDIA realized that this operation is actually quite costly itself. So now not only there are specialized instructions for matrix multiplication, there are now also specialized instructions for calculating the offsets within a larger tensor. And to make things worse, there's tensor memory accelerator on Hopper, but on Blackwell, the next NVIDIA GPU, there's a completely separate, almost identically called set of instructions called TMEM. And what they do is a separate talk for another couple of hours, but happy to chat afterwards. So what are our conclusions? First thing that happens on the hardware and software side is that like one side cannot just win. You need like a combination of software and hardware work. There's a lot that's happening that I haven't even touched in this discussion. But one of the default things that we used to do, like in conjunction between software and hardware vendors, is actually tune the tile sizes so we can actually saturate the caches on the chip more efficiently. That has been around for decades, and that's not something super new. Then we now see an introduction of 2D registers, let's call them that way. So like instead of vector instructions, we now have matrix instructions, and we would all be wiser to use them. Sadly, not all the software does. Another weird thing is like how incapable our compilers are, and even like HPC developers, of like finding those ways to interleave independent instructions for CPU port utilization and GPUs as well. It's not always going to be a game changer, but in some scenarios it can yield a 70% improvement. So if you're building something like a $500 billion data center, or like $500 billion worth of data centers over a few years, like OpenAI is planning, 70% difference in hardware utilization is a huge deal. It's like comparable to the combined GDP of the bottom of the UN list. And the last but not the least, we're now about to enter the era of new kind of asynchrony where debugging software is practically impossible and it's implemented in hardware. All of those can be used outside of matrix multiplications. I just thought it's a really cool example to showcase the setup. And to summarize, many of those tricks went into the projects that I maintain, including those 4 libraries. So usearch may just be the world's most deployed vector search engine with bindings for 10 programming languages that powers a lot of the database companies that you use every day. ucall is a prototype of an RPC implementation that uses kernel bypass on Linux 6.0 and newer, and I will be talking about it tomorrow briefly. Stringzilla is 3 times faster string implementation than the libc standard library, and SimSim is my mixed precision numerics library that hopefully will be more and more compatible with NumPy as they get low precision numeric types down the road. I occasionally invest in deep tech companies, so if you ever need advice on like how not to do pitch decks, I know everything about it. Drop me a line, and thank you for participating in this. I'm open to questions.
Great, thank you, Ash. I think we have a question.
Hi, great stuff, Ash. Thank you. Have you been following the accelerated discussions for RISC-V, and have you got any thoughts around what people are doing there and which directions should be gone in?
Yeah, absolutely. RISC-V is amazing. So like RISC-V is the open source instruction set. I guess many of us are here familiar with it. They have vector extensions as well, RVV. I've only seen one project that uses them, and sadly, it's not one of mine, but it's a peer in the community. So there's like the SIMD UTF project, I believe, maintained mainly by Daniel Lemire, and they submitted a patch for RISC-V about a year ago. But one of the core things about this kind of work is you need to have hardware on hands. And the lack of RISC-V hardware and its availability, especially anything with high core counts, makes it practically infeasible for me to like also expand onto that platform. Though I'm very excited and can't wait to see new results.
Yeah, let's see what happens.
Yeah.
Thanks.
Anyone else? Oh, okay. You can find me afterwards during the conference. I'll be around. Thank you.